Section 10.7, complex numbers. So let's recall when we tried to solve the equation, let's say x squared plus 1 equal to 0, we found that, well, if I try to solve this over the reals, I get that x squared equals -1, but then I would try to make sense of x equaling plus or minus the square root of -1. Well, we can't solve this with real numbers. Because if you take any real number and you square it, there's no way you're going to get a -1 as a result. So let us introduce a new field of numbers, the complex numbers. We'll define the complex numbers as following. Let C denote the field of complex numbers. It's just going to be the cross product of the real numbers crossed with the real numbers. So let us endow this field of complex numbers with the following algebraic operations. So if I have AB and CD being members of the complex field, so let's say A, B, C, D are real numbers, then I can define addition of two complex numbers as follows. It's just equal to A plus C, comma, B plus D. We can also define multiplication of two complex numbers as follows. AB times C comma D is just AC minus BD comma AD plus BC. Okay, so that's my those are my operations. In order for this to have the field properties, let me also give you some names for certain quantities. I'll call the additive inverse the additive identity. So the additive identity for this complex field is just the ordered pair 0, 0. The additive inverse of some complex number AB is, well, minus A comma minus B. The multiplicative identity for this field of complex numbers is the ordered pair 1 comma 0. The multiplicative inverse of some complex number AB, and I'll assume that AB is non-zero, is, well, let me denote the multiplicative inverse with this superscript. And so it's just equal to the following the following ordered pair: a over a squared plus b squared, comma, negative b over a squared plus b squared. Let me give you some notation. Let us define subtraction as follows: AB minus CD is just equal to, well, AB plus the additive inverse. So AB plus minus C minus D. And similarly, I'll let AB divided by CD just equal AB times the inverse of CD. If, well, CD is not 0. Because, of course, we don't want to divide by 0. Okay. Now, let us note the following. Let I denote the ordered pair 0, 1. And so, let's also let the ordered pair AB, instead of writing the ordered pair AB, let's write in new notation. Let's write in the notation A plus BI, where of course A and B are real numbers, as we've said before. Then note the following. I squared, which is 0, 1 times 0, 1 is equal to, well, from the above, I just get 0, 1 times 0, 1 is 0 times 0 minus 1 times 1 comma 0 times 1 plus 1 times 0. And so that's equal to 0 minus 1, which is a negative 1, 0 plus 0, which is 0, which I can write as, well, using this above notation, it's a negative 1 plus 0 times I, and so negative 1. And so what I've shown here is that I squared equals negative 1. And so we've made sense of something that could satisfy this equation. Because if you just plug in I, you get that I squared plus 1 is 0. And so we can actually make sense of the square root of negative 1. And so, in other words, we can think of I as being the square root of negative 1. And so we've made that sort of concept understandable. So from now on, we'll just say that the complex numbers, C, consist of numbers of the form a plus bi, where a and b are real numbers, and the only property we really have to know is that I squared is -1. So from all the above, really that's all the important things I need to take away from those definitions above. And so, and you'll notice that if you use that fact, all the stuff that I've written above will be consistent with this notation. The standard form of a complex number is, well, what I've just written. So suppose I have some complex number z. I can write it in the form a plus bi, where a is the real part of z is just the number a. So this is the real part of z. And b is the imaginary part of z. Note that a and b are real numbers. And so the imaginary part of a complex number is a real number. We denote the real part by RE of the complex number. We denote the imaginary part of a complex number as IM of that complex number. Okay. Now, let us note the following pattern. So note that I to the 0 is 1. I to the first is I squared. Well, we said that I squared is -1. I cubed is just I squared times I, but I squared is -1 times I is -I. I to the fourth is just I squared times I squared, but I squared is -1 times -1 is +1. I to the fifth is just I to the fourth times I, but I to the fourth is 1 times I is I. I to the sixth is, well, I squared quantity cubed, -1 cubed is -1. I to the 7 is I times I to the 6, but I to the 6 is -1 times I is -I. I to the 8 again is, well, I squared to the power 4. I squared is -1 to the power 4 is 1. I to the 9 again is I times I to the 8, which is 1, so I times 1 is I. I to the 10 is, well, I times I to the 8, but I times I to the 9. I to the 9 is I, so you get I squared, which is -1. I to the 11. Well, look at the pattern, you get negative I to the 12 is 1, I to the 13 is I to the 14 is negative 1, I to the 15 is negative I, etc. So if you look at this pattern, well, this pattern continues. And so we have the following. So let n here be a natural number. Let's say it's a whole number. Actually, I can let it be an integer. Let n be an integer. Then I to the power n is 1 if n mod 4 is 0, I if n mod 4 is 1, negative 1 if n mod 4 is 2, negative I if n mod 4 is 3. Okay, let me explain that notation, modulo. And so, if I look at the number, let's say 23 mod 4, well, 23 mod 4 is the remainder of 23 divided by 4. And so the remainder of the quantity 23 divided by 4 is the number 3. And this is since, well, 23 is 4 times 5 plus 3. This is the division algorithm. The dividend, so we did this before. The dividend is the divisor times the quotient plus the remainder. Okay, and so, well, let's say n mod divisor, so n mod d is equal to r. If there is a quotient such that n is equal to q times d plus r, and I'll pick the particular remainder where it's the standard remainder, where this remainder here is some natural number less than the divisor. Let me actually just do this for, yeah. So I'm not going to be dividing by 0. So, well, it could have a 0 um, where n is less than the divisor. And of course, where r is less than the divisor, the remainder is less than the divisor, and where r here is a natural number, a whole number. I'll just do this for whole numbers. Okay, so let me give you an example of what that is telling us. So suppose I looked at I to the power 23. Well, 23 is just 4 times 5 plus 3, right? That's what we saw. 23 is 20 plus 3, which I can write I to the power 4 times 5 plus 3, which is I to the 4, the power 5 times I cubed. What? I to the 4th, I squared times I squared. Negative 1 times negative 1 is positive 1. And so I to the 4th is always 1. So we use the fact that I to the 4th is always 1. That's why we worry about, why we don't need to worry about any multiple of 4. So if I get rid of all the multiples of 4, I take the modulo. All I'm doing here is getting rid of multiples of 4. Okay. Then all I have to do is remember what I cubed is. So all I have to do is remember, well, what's either 0, 1, 2, and 3. So either 3 as well, negative I. Or you can say, well, it's I squared times I, which is a negative 1 times I, negative I. So what you should take from this is the following. If you want to do I to the 23, you just get rid of any multiple of 4, and you remember that, well, I cubed is negative I. And then you're done. And so you can sort of cut down all of these intermediate steps by just noting that fact that you don't really have to worry about multiples of 4 because I to the 4th is 1. So let's do some examples from the book. Let's do on page 407. I don't know. Let's do problem number 407. That's not correct. Problem 44. I'm sorry. That's a 443. So on page 443, let's do problem number 5. I to the power 7. In exercises 1 through 10, simplify the expression where I is equal to the square root of negative 1. Well, just get rid of any multiple of 4. Well, and so I to the 7th is the same as I cubed. You can subtract from it 4. And well, I cubed is, well, we just saw it above, is I squared times I. And I squared is negative 1 times I is negative I. And so if you memorize that I cubed is negative I, you're done. Next, let's do problem number, let's say 7. I to the 27. Let's get rid of any multiple of 4. Well, I can subtract from it 6 times 4, which is 24. So 27 minus 24. So I can get rid of any multiple of 4. And so this is equal to, well, let me just write it as 6 times 4. And so having any multiple of 4 doesn't make any difference. And so this is the same as I to the 3. But I already know what I cubed is, negative I. Let me do problem number, let's say 8. I to the negative 15. Again, adding or subtracting any multiple of 4 doesn't make any difference. So let's add to it 16. So 4 times 4 is 16, minus 15 is 1. And so I to the 1 is, well, any number to the power 1 is itself. And so I to the 1 is I. Let's do problem number 10. I to the 82. Well, 82, if I subtract 80 from it, I to the 82 minus 4 times 20. So again, I'll get rid of the multiples of 4. And so 4 times 20 is 80. 82 minus 80 is 2. So I get here I squared. But again, I squared is negative 1. And so I to the 82 is negative 1. Okay. And so note the following. If I have here some number, let's say b, greater than or equal to 0, then the square root of negative b is equal to the square root of negative 1 times the square root of b, and the square root of negative 1 is I. So if I want to take the square root of a negative number, I just take I times the radical of the absolute value of that number inside the radical. So let me do problem number 11. The square root of negative 4. Well, that's just equal to I times the square root of 4, but the square root of 4 is 2. And so this is equal to, the square root of negative 4 is equal to 2I. Let me do problem number 14. Square root of negative 18. Let me write negative 18 as negative 9 times 2. The square root of negative 9 is 3I, and I have a radical 2 remaining. So 3I rad 2. Let me do problem number 17. Radical 4 plus radical 4 times negative 2. Times radical 4 plus radical negative 4. So in exercises 17 through 22, write the complex number in standard form. Identify the real and imaginary parts. The square root of 4 is 2. The square root of a negative 4 is 2I. Since 2 squared is 4, I squared is negative 1. This is written in standard form. And so now let us write down the real part and the imaginary part. So the real part is, well, 2. That's the number that does not have an I. The imaginary part is 2 also. It is the number in front of I. So the real part is this number. The imaginary part is that 2. Okay? Let me do problem number 22. The square root of negative 13. So this is just square root of a negative number. It's just I. We're at 13. That's written in standard form. You usually don't write it as 0 plus I rad 13. So that would be the real part and the imaginary part. Usually you just write it where, if there's some part that's 0, then you just leave it unwritten. And so, let me keep it in this form. Let me write down the real part and the imaginary part. Well, there is no real part. It's 0. The imaginary part in this particular case is rad 13. And that is my answer. Okay. Let me do problem 23. Three plus 7i plus 4 minus 3i. In exercises 23 through 36, perform the indicated operations. So, let me remove the parentheses, and let me just combine like terms. Well, 3 plus 4 is 7. 7i minus 3i is a positive 4i. So you just combine like terms. Notice that I'm adding the real parts, adding the imaginary parts. So if you look back in our rather strange definitions from the beginning, what we did is to add two complex numbers. We added the real parts, we added the imaginary parts. And that's how that definition came about. It was just using that fact. Let's do another one. Let's do problem number 28. Four minus 7i plus 3 plus 5i minus 2 plus 9i. And so I can just get rid of all the parentheses. All we're doing is adding and subtracting. So this is 4 minus 7i plus 3 plus 5i. Now, since I'm subtracting, I've got to change all the signs inside the parentheses. And so let me do that. Let me make that a little nicer. Okay, so this negative changes the positive 2 to a negative 2. This negative changes the positive 9i to a negative 9i. And now let's combine like terms. 4 plus 3, 7 minus 2 is 5. Negative 7i plus 5i is negative 2i minus 9i is negative 11i. And that is your answer. Let me do problem number 31. Negative 2 plus 7i, 2 plus 5i. And so let's multiply using distributive property. And so I get negative 2 times 2 is a negative 4. Negative 2 times 5 is a negative 10i. 7i times 2 is 14i. 7i times 5i is a positive 35i squared. And so I get a negative 4 minus 10i plus 14i. I'll use the fact that I squared is equal to a negative 1. And so I'll replace I squared here by negative 1. So I get a negative 1 times 35 minus 35. And now let me combine like terms. So I get a negative 4 minus 35, negative 39. Negative 10i plus 14i is a positive 4i. And that is your answer. Also note that this makes sense of what we did above. So notice we did first times second to get the negative 4. Then we did these last two. So the first we multiplied, then the last ones we multiplied. But when we multiplied those together, we changed this to a negative and we combined them. Then we multiplied the first and seconds of each of them and combined them. And so, if I look up here, that was this definition. Oh, here it is. So notice we multiplied each of the first, but then we and that was in the first part of it. That was the real part. But then we multiplied the imaginary parts, and when we did that, we put a minus sign, and that was because the I squared was negative 1. And then we multiplied the real and imaginary parts and added them together, and that gave us the imaginary part of the product. So the real part times imaginary, the imaginary part times the real part. And so that's how we multiply. And now that definition makes sense. You just multiply it out. Use distributive property and use the fact that I squared is negative 1. Okay. Let's do problem number 36. 7i times 2 plus 3i minus negative 4 plus 5i. Okay, so let me just get rid of the parentheses here. So if I do that, I get 7i times 2 plus 3i. Now I have a minus out in front, and so let me change the signs inside the parentheses. So the negative 4 becomes a positive 4. And the positive 5i becomes a negative 5i. Now let me combine like terms. And so I get 7i times 2 plus 4 is 6. 3i minus 5i is a negative 2i. And now let me multiply the 7i inside the parentheses. And so I get 7 times 6, 42i. Positive times negative is negative. 7 times 2 is 14. I times I is I squared. And again, I use the fact that I squared is negative 1. So I'll replace I squared by negative 1. Negative times negative is positive. So this negative 14i squared becomes a positive 14i squared, a positive 14. And the 42i remains the same. Now, we usually like to write these in standard order. So I write the real part first. So it's a 14 plus 42i. And that's your answer. Next, the complex conjugate. So let z be a complex number, say a plus bi, where a and b are real numbers. Then the complex conjugate of the complex number z will be noted by z with a bar over it. And it's just going to be the real part minus the imaginary part times I. And so the complex conjugate of a plus bi is just a minus bi. Note the following. That a complex number times its complex conjugate, a plus bi times a minus bi, well, I can simplify this. Let's use the distributive property, and let's multiply this out. So I get a times a is a squared. A times minus bi is a minus abi. Bi times a is a positive abi. Bi times minus bi is a negative b squared I squared. Use the fact that I squared is negative 1 to replace I squared by negative 1. We get, well, a squared. The ABI's cancel. Minus b squared times I squared. I squared is negative 1 times your minus b squared becomes a plus b squared. So notice that if you multiply a complex number times its complex conjugate, you get a real number. So this is a real number. So if you want to get rid of the imaginary, the fact that, there's some imaginary part there, you just multiply by the complex conjugate and you get a number without an imaginary part. So let's do some examples. Let's say problem number 37. 2 minus 5i. In exercises 37 through 42, write the complex conjugate of the complex number and verify that the complex number times its conjugate is the square of the real part plus the square of the imaginary part. Okay, so let's do that. And so let's find the complex conjugate. So the complex conjugate will just equal the same real part, but I change the sign of the imaginary part. And so the complex conjugate of 2 minus 5i, oh, I don't like that location. Let me move this over because it looks like I'm dividing. Okay, so let me move this way out the way. Okay, yeah, I like that much better. Okay, so the complex conjugate of 2 minus 5i is just 2 plus 5i. So you just change the sign of the imaginary part. Now let us show that a number times its complex conjugate will be a real number. And so this is one of the special product formulas. So let me note that this was the special product formula above. And so this is the product, the sum and difference of two terms. So let's multiply this. 2 times 2 is 4. Minus 5i. Minus times positive is minus. 5i times 5i is 25i squared. Let me use the fact that I squared is negative 1 to simplify this. And so I get negative 25i squared becomes a positive 25 plus 4 is indeed 29. And so a number times its complex conjugate is the square of the real part, the square of 2, plus the square of the imaginary part, 5, and so 5 squared is 25. Let me do problem 42. And so I have the number 5, and I want to find the complex conjugate of 5. Well, the complex conjugate of 5 is still 5. I've changed the sign of the imaginary part. And so let's do 5 times 5 is 25, which is the real part squared. Okay. Plus the imaginary part squared. Well, the imaginary part is 0. And so 5 squared is indeed 25. Let me do problem number 43. So 43, 1 over 2 minus 5i. In exercises 43 through 50, find the quotient and write your answer in standard form. Okay, so I want to write this in standard form, but I want to get rid of the complex part in the denominator. And so to get rid of this the I in the denominator, let's multiply and divide by the complex conjugate. Because we noted above, the way to get rid of the I was just to multiply by the complex conjugate. So let's multiply by the complex conjugate of the denominator, which actually is right here. The complex conjugate is a 2 minus 5i. So let's do that. Let's multiply by 2 plus 5i and divide by 2 plus 5i. Well, 1 times 2 plus 5i is certainly 2 plus 5i. 2 times 2 is 4. Negative times positive is negative. 5 times 5 is 25. I times I is I squared. And again, I squared is a negative 1. And so this is equal to 2 plus 5i divided by 4 plus 25 is 29. And usually we would write it like this. But you want to write in standard form. So this is equal to 2 over 29 plus 5 over 29i. And now note that this explains another one of our weird sort of formulas I gave above. And so notice that if you have I'm taking the reciprocal, the multiplicative inverse of the complex number 2 minus 5i, and well, the answer was the real part over, well, notice this is the square of the real part plus the square of the imaginary part. Oh, okay, so a over a squared plus b squared. And whereas this is the opposite sign of the imaginary part. So a minus b over b squared, a squared plus b squared. And so notice we had a definition of, here it was. The multiplicative inverse, the reciprocal, was, well, the real part of this inverse was the real part of the complex number over a real part squared plus imaginary part squared. Then the imaginary part was the negative of the imaginary part over real part squared plus imaginary part squared. And therefore that makes sense. That's what we have done in this problem. And so the only fact that I really needed was the fact that I squared is negative 1. And then you do all the same sort of arithmetic you've done in the past. And so that all those weird definitions make sense. They're just do what you've always done, but use the fact that I squared is negative 1. Let's do problem number 46. Negative 4i over negative 2 plus 3i. Okay, so I want to rationalize the denominator. So I want to get rid of the I in the denominator. So let me multiply and divide by the conjugate of the denominator, negative 2 minus 3i. And divide by the same quantity, negative 2 minus 3i. And so let's multiply. And so if I do that, I get the following. Negative times negative is a positive. 4 times 2 is 8i. Negative times negative is a positive. 4 times 3 is 12. I times I is I squared. Negative 2 times negative 2 is a positive 4. Positive times negative is negative. 3i times 3i is 9i squared. Use the fact that I squared is a negative 1. And so this becomes the positive 12i squared becomes a negative negative 12. The 8i remains the same. The negative 9i squared becomes, well, positive 9. And 4 plus 9 is 13. And again, I usually just leave it in this form, but let's write it as a negative 12 over 13 plus 8 over 13i. Okay, let's do one last one, I guess. Actually, let me do two more. Let me do problem number 49. Two plus I over 4 minus 5i. So let me rationalize the denominator. So let me multiply and divide by the complex conjugate of the denominator, 4 plus 5i, and divide by the same quantity, 4 plus 5i. Let me multiply. 2 times 4 is 8. 2 times 5i is 10i. I times 4 is 4i. I times 5i is a positive 5i squared. 4 times 4 is 16. Minus 5i times positive 5i is a negative 25i squared by the special product formula. The product of the sum and difference of two terms is the difference of their squares. I'll use the fact that I squared is a negative 1, so I get 8 plus 10i plus 4i. Since I squared is negative 1, 5i squared becomes a negative 5. Since I squared is negative 1, negative 25i squared becomes a positive 25. 8, combined like terms, 8 minus 5 is 3. 10i plus 4i is 14i. 16 plus 25 is 41. And again, let me write this in standard form. 3 over 41 plus 14 over 41i. And so the square root of 3 plus 4i over 2 plus 5i. Let me rationalize the denominator. So let me multiply and divide by the complex conjugate of the denominator, 2 minus 5i. Radical 3 times 2 is 2 radical 3. Radical 3 times a negative 5i is a negative 5i rad 3. 4i times 2 is 8i. 4i times a negative 5i is a negative 20i squared. 2, again, using the special product formula, that the product of the sum and difference of two terms is the difference of their squares. 2 times 2 is 4. 5i times negative 5i is a negative 25i squared. And so I have 2 rad 3 minus 5I rad 3 plus 8I. I'll use the fact that I squared is negative 1. So negative 20I squared becomes a positive 20. Let me use the fact that I squared is negative 1. So negative 25I squared becomes a positive 25. And so I have that this is equal to 2 rad 3 plus 20 is just 20 plus 2 rad 3. 8I minus 5I rad 3 is, well, 8I minus 5I rad 3. 4 plus 25 is 29. And so this is equal to, well, maybe I'll just write it as the real part, 20 plus 2 rad 3 plus the imaginary part. Let me factor out the I, 8 minus 5 rad 3, I, all over 29. And lastly, let me write it in standard form. So let me write it as 20 plus 2 rad 3 all over 29, the real part, plus 8 minus 5 rad 3 all over 29, I. And so the imaginary part. And now I've written this in standard form. Usually I would just write it in this form. If I didn't need to write in standard form, this is probably the form that is most likely to be useful. Okay, so that finishes off section 10.7, which means we only have 7 minutes. So I guess that's it for today, because we don't have enough time for anything else. Okay, then. That's it. Let me stop the recording.